So orders, rate equations, and rate constants. So let's think about what we learned last year for the definition of rate of reaction. Rate of reaction is the rate of change in product produced or reactant used up. Okay, so we learned rate of reaction as the amount of product formed over time or the amount of reactant used up over time. In general, you can combine both of these to give this equation. Rate of reaction is equal to change in concentration over time. Or you can just say that the rate of reaction is the change in concentration of a reactant or product per unit time. And the units for this are moles per dm cubed seconds to the minus 1. So that's the units for the rate of a reaction. So let me make you aware of notation that you use in chemistry. So square brackets with a letter in it, like this, that basically means the concentration of A. So that could be a product or it could be a reactant. So if I use this from now on, if I use square brackets, just know that it means concentration. So let's say that we have a concentration against time graph, and on the y-axis we have the concentration of A, and on the x-axis we have time. And our graph goes roughly like this. So if you want to work out the rate of the reaction at a particular point, so let's say around here, we want to work out the rate at this point, what we need to do is find the change in concentration over time. So if you think about it, because you've got change in concentration as the y-axis and time as the x-axis, so your rate is change in concentration over time according to the definition. So that's basically saying the change in y divided by the change in x. And from maths you might remember, so maths GCSE, you might remember, if you do change in y over change in x, that's basically the gradient. So the gradient of a concentration time graph gives you the rate of a reaction. So for this example here, to work out the gradient of a curved line, what you'd need to do is draw a tangent. So a tangent has to touch the curve at one particular point, like so, and then you need to work out the gradient of the tangent using change in y over change in x. So change in y over change in x. And by doing that, you can work out the rate at that particular point. So moving on now, we're going to talk about reaction orders. And what a reaction order tells you is how rate is affected by concentration. So you can have different orders of a reaction. So the lowest order you can have is a zero order reaction. So in a zero order reaction, what that means, if you double the reactant's concentration, the rate does not change. In other words, whatever you do to the concentration, if you double, triple, quadruple it, the rate of the reaction doesn't change at all. So if you have a zero order reaction, it's not affected by the concentration of the reactants. So another way to say this is rate is proportional to the concentration of reactant A to the power of 0. The reason that is because if you put anything to the power of 0, it equals 1. So rate is proportional to 1, which means rate doesn't change. So the rate always stays the same. So whatever you do to the concentration of the reactants in the reaction, the rate will not change. So that's when you have a zero order reaction. What you can also have is a first order reaction. So that's when if you double the reactant's concentration, the rate also doubles. So if you triple it, if you triple the reactant's concentration, then the rate will also triple. So in other words, the rate is proportional to whatever you do to the reactants to the power of 1. So again, let's imagine you're doubling it, so you're timesing this by 2. So your A is basically times by 2. Then you're doing 2 to the power of 1, which is 2. So you're just timesing the rate by 2 as well. Or another thing you can say is rate is directly proportional to concentration. So whatever you do to concentration, same thing happens to rate. And then the next one you need to know is second order reactions. And in a second order reaction, if you double the reactant's concentration, the rate quadruples. So the reason for that is because the rate is proportional to whatever the reactant concentration is squared. So that means if you double the reactant's concentration, then the rate is going to double it squared. So 2 squared is 4, so it's going to be 4 times greater. So that's why it quadruples. If you triple the reactant's concentration, you times it by 3, then your rate is going to be times 3 squared. So your rate will increase by a factor of 9. So that's how you work out how the rate changes with concentration. It'll become more clear when we start looking at some examples. So you also need to know how the graphs for these look like. Okay, so for every order that you have, your 0, your first or your second order, there is a concentration time graph or a rate concentration graph that you need to know. So for a 0 order graph, the concentration time graph should look like a straight line downwards, because remember, concentration doesn't affect rate, so the gradient should not change with this. The gradient should stay the same. For first order graph, it should be curved. So something like this. For a second order graph, it will also be curved like the first order graph. It will just be slightly steeper. So it could look something like this. So it's hard to tell the difference between a first order and a second order reaction by looking at the concentration time graph, because they both look very similar. But you can look at 0 order and a first order graph and tell the difference, because a 0 order graph is straight and a first order graph is curved. Now for the rate against concentration graph, if you think about it, remember 0 order concentration does not affect rate, so this should be horizontal line. So no matter what the concentration is, the rate should always stay the same. For a first order graph, we said it was directly proportional. Directly proportional in science, remember, that means it's a straight line through the origin. And for a second order graph, it's a curve upwards. So when it comes to rate concentration graphs, it's easy to tell the difference between all 3 of them, because they all have different shapes. But for concentration time graphs, you can only tell the difference between a 0 order and a first order graph. So now we're going to look at how it's possible to work out the order of a graph experimentally. So there's 2 methods to do this. The first one that you'll come across is the half-life method, but this doesn't prove any order. The only thing this does is it proves whether something is first order or not. It doesn't prove whether something is second order or third order or anything else. It only proves whether something's first order or not. The definition for half-life is the time taken for the initial concentration of a reactant to half. So let's say we have the following graph where the concentration of A is decreasing with time, and we want to figure out whether this is first order or not. So in an exam, what they're most likely to do is to give you an actual graph like this. So they've said they've done an experiment and they've monitored the concentration of a particular reactant every second or so, and they've plotted this graph from that. Now from this graph, you need to be able to work out whether the reaction is first order with respect to this reactant or not. So to do that, first of all, you've got to notice that this top point here is the initial concentration. So what you want to do, remember the definition of half-life is the time taken for the initial concentration of a reactant to half. So you need to go to half of the initial concentration. So it'll be around here, but in a real exam question, they'll actually give you a number. So let's say that was 100 moles per dm cubed, then you'd go down to 50 moles per dm cubed. If that was 90, you'd go down to 45, so whatever it is. And you've got to basically work out the time it takes for it to half. So you get a horizontal line, use a ruler, and draw it all the way up to the curve, and then draw a vertical line down to the bottom. and then see what time this is at. This will give you your first half-life. But to prove that something is first order, you need to prove that the half-life stays constant. So only for graphs which are first order will you have a constant half-life. So what you need to do after that is you need to go to a quarter of the initial concentration. So you need to half it again to find what the second half-life is. So I'll draw that one with a solid line. You go across, and then you go down again. And then once again, you find out the time that that takes. And what you basically got is the second half-life. So if your first half-life is equal to your second half-life, then you've got a first order reaction. If it's not, then only thing you can say is that it's not a first order reaction. So if the half-life is constant, so if your first and your second half-life are the same, then the reaction is first order with respect to reactant A, because reactant A is what the graph is all about. It doesn't mean the whole reaction is first order, it just means that reactant A is first order within the reaction. So that's the first method of proving whether something is first order or not. From this method is also something else you could calculate, which we're going to look at in a bit, which is known as the rate constant, K. And to work out K, whatever your half-life value is, you just do ln of 2 divided by your half-life. We'll call that T half. So ln 2, if you put into your calculator, is around 0.693. If you divide that by whatever your half-life is, you get the rate constant, which I'll be explaining in more detail in a second. So this is the first method on trying to figure out what order a reaction is. The second method is much better for figuring out whether it's zero first or second order. So this one only proves whether something's first order or not, but the second method proves more than that. And the second method is known as the initial rate method. So let's say again we have a graph of concentration of A against time. If we wanted to work out the initial rate from this graph, initial would be at this point here. We want to work out the rate. Remember, in a concentration time graph, the rate is basically the gradient. What you'll do is draw a tangent at that point. So whatever gradient that's at, like so, and then find the gradient of this tangent. Now, by finding the initial rate for loads of different experiments, you can figure out the order with respect to each reactant. But to do that, you need to do loads of experiments and only change one reactant and keep everything else constant. So what I'm going to do now is I'm going to draw a table of results. So let's say we have the following reaction occurring, and we want to work out the order of the reaction with respect to each reactant, so NO, CO, and O2. So if you want to do this experimentally, you can do this by doing 4 different experiments. So for the first experiment, you choose specific initial concentrations for each reactant. So I'm going to draw a table to note down an example of initial concentrations. So we've got all 3 reactants here, NO, CO, O2. We've got the initial concentrations measured in moles per dm cubed, and the initial rate measured in moles per dm cubed seconds to the -1. So let's say we carry out this experiment, this reaction, and we choose specific initial concentration of each reactant. So for NO, we pick 2 times 10 to the -2. For CO, we pick 1 times 10 to the -2. And then for oxygen, we pick 1 times 10 to the -2. Okay, so we do this reaction, we monitor everything that's happening, and we draw a graph of the concentration against time, like this, and then we work out the initial rate by finding the tangent and working out the gradient of the tangent. So we do all of that, and then we get our initial rate to be 0.176 mole per dm cubed per second. Okay, then we do a second experiment where we only change NO, the concentration of NO at the start. So this is 4 times 10 to the minus 2. So what we've done is we've doubled NO, but we've kept everything else the same. And then we do exactly the same thing. So we draw the graph again and then find the gradient of the tangent, and we get that as 0.704. Next, we repeat it again, but this time we change what CO is instead of NO. So we'll use the initial value of NO that we used. CO we change to 2 times 10 to the minus 2, and then O2 we keep the same. So everything needs to be kept the same apart from what it is that you're trying to figure out. And that gives you a rate of 0.176 as well. And then for your fourth experiment, you want to look at oxygen. So you keep NO and CO the same. So 2 times 10 to the minus 2. When I say the same, I mean the same compared to experiment 1, by the way. So this would be 1 times 10 to the minus 2. And this time you change just the oxygen and make that, 2 times 10 to the minus 2. And we do the same thing again. We work out the initial rate and we get it as 0.176. So in an exam, you probably won't be asked to draw a table like this and to fill out the initial rate. This table will most likely be given to you in the exam, and they'll ask you to work out the orders from this table. So to do that, what you need to do is you need to compare different experiments. So let's say we want to work out the order of the reaction with respect to NO. So what you do is you compare experiment 1 and 2. So what's happening in experiment 1 and 2? Your NO is increasing by a factor of 2, and your rate, so from 1 to 2, if we look up, your NO is increasing by a factor of 2 from 2 to 4, but your rate, if you work this out, increases by a factor of 4. So this is increasing by 2, this is increasing by 4, which is basically the same as 2 squared is increasing by 2 squared. So from this you can figure out that the reaction is order 2 with respect to NO, because you're doubling NO and that's causing rate to quadruple. So if you look back at your notes, earlier on we said that if you have this case, then it means that it's second order. So your conclusion is reaction is second order with respect to NO. Then you can do the same for the other two. So for CO, you can compare experiment 1 and 3. So when you do that, your NO is staying the same, your CO is increasing by 2, and your rate is staying the same, so it's increasing by 1. So now when you do that, you've got to think about what that means in terms of its order. So CO is doubling, but the rate is staying the same. It's timesing by 1, which is basically times 2 to the power of 0. So that tells you that this is a 0 order reaction. And if you do the same for oxygen, you should find the same thing. You compare experiment 1 and 4. What you find is that oxygen doubles, but the rate stays constant. It's multiplied by 1. So same thing again, it's multiplied by 2 to the power of 0, which tells you that's also order of 0 with respect to O2.
For more videos like this, summary videos, worked examples and exam tips, subscribe to my channel.